All right, so let's continue with this. So this is kind of where the last video left off. But by the way, the reason I use they're only in 15-minute increments is because the program that I use to create these videos, this is the free version. So the free version gives me 15 minutes at a time. So that's why they're like that. Anyhow, that's beside the point. So gold is a soft mineral because, and we just I was just talking about that because the atoms are very large. So the larger the atoms, the softer the mineral. So all right, let's see. So there it is. There's the right answer. We'll return to this idea about cleavage and fracture. Remember, they're kind of like opposites of each other. So cleavage is a property of a mineral that breaks along planes of weakness, right? Planes of weakness are determined by the crystal structure. Basically, you might have strong bonds. Let's say if just watch what I'm doing with the mouse here. If you go this way along these sentences, but between the sentences, let's say that those bonds are relatively weak. And so, I could peel off this top sentence, not the sentence obviously, but, if these four lines here were a mineral, like mica or something like that, I could peel off the first one. You can actually, with mica, again, you can do it just with your fingers. It's so weak that the bond between the layers. Yeah, that's a good way to look at it. All right. But the within the layer, like from word to word, if you will, along one of these sentences, those bonds are very, very strong. It's the bond that when you go from sentence to sentence or layer to layer. That's a good way to look at it. All right, so fracture, and I know I've already said this, but let's just make sure that we all understand this. So fracture occurs when a mineral bond's strength is generally the same, right? So if the bonds are the same in all directions, and I I break something, then what's going to happen is it'll break in just kind of a bizarre, well, not bizarre, but just a not a predictable way. Like with when a mineral has really good cleavage, it'll always break along those planes. But fracture, it might break in a kind of a diagonal type of, that's just an example, a diagonal line, or, they talked about with obsidian, you could have a conchoidal where it's kind of curved a little bit, like that volcanic glass. All right, so that's just an example. So these are like extremes. If something has strong cleavage, it's not going to fracture. If something has no cleavage, when you say that there's no overall cleavage, that means the bond strength is relatively the same, and so it's going to fracture. All right, so those are stuff to remember. All right, color is an obvious feature for many minerals, but again, I mentioned this before, it's not a reliable mineral identification. All right, so chemicals can have these little impurities, and so the little impurities between like ruby and sapphire, I think one of them has titanium. I think that's this one. I can't remember actually. One of them has more titanium, and one of them has more. What is it? One's titanium, and one is iron. Yeah, the other one's iron. If I'm remembering that correctly. All right, so that it's just remember that you can have the same thing. You can have something that's quartz, and yet if it has little slight variations in minerals, it'll be a different thing. And by the way, you notice we have these, something called a ruby or a sapphire. I mean, these kind of things can be expensive because they are what we consider, they're precious. They're gemstones. Sometimes people call them gems. And that has to do with what's called the luster. We'll get into that in just a little bit. Like diamonds have a really good luster. And we already covered this. Density is the mass divided by the volume. And remember, what we generally do is the mass is in grams, the volume is in cubic centimeters. Let's see. So the more dense things will feel heavier if they're roughly the same size. All right. Physical properties of a mineral are predominantly related to. All right, so is it going to be external conditions of temperature, pressure, and the amount of space for growth? So remember that has to do with how the crystals form. That's not going to be the physical properties. The chemical composition of and the internal arrangement of the atoms that make up the mineral. So that seems to be very likely. Crystal form, hardness, cleavage, right? So that's just describing, what's going on with the mineral. So B, right? The physical properties of the mineral are predominantly related to the chemical composition and the internal arrangement. So B is the proper answer. All right, let's move on. The color of a mineral is predominantly related to, is it going to be chemical composition, internal arrangement, the luster, or the temperature and pressure conditions at the time of composition? It's actually the chemical composition. There are two classifications of minerals. Okay, so I kind of hinted at this a little bit before, but we got to understand this. So there are silicates, right? Silicate minerals and non-silicates. Okay, so notice right away, silicate minerals, you're talking about 90% of the crust, right? And we really only have access, to the crust except for volcanic eruptions, right? When the magma comes up from the mantle of the earth, then in liquid form, obviously, then we have access to material in the mantle. But usually, we're encountering silicate rocks, right? Well, silicate minerals, I should say. We're not quite to rocks. We're going to get there in just a little bit. Remember, rocks are made from minerals. All right, so that's why we're spending some time now talking about minerals. So silicate minerals are made of, I know, big surprise, silicon and oxygen, right? All right, and then you have these other elements that are common. Most of them are common. Aluminum certainly is common in the crust. Aluminum, magnesium, iron, manganese. This is not quite as common, and titanium. Right, titanium can the different amounts of these metals. These are all metals. Can change the color of these things, or the chemical composition, basically. All right. All silicate minerals have the same fundamental structure, and it's called a tetrahedral. So I showed you a picture of this earlier, but you definitely want to remember this. Okay, so these are the silicon atoms outside, and I'm sorry. This is the silicon atom in the middle. That's a big difference. And these are the oxygens outside. All right, so. All right, so tetrahedral, it's kind of like a pyramid shape, but in 3 dimensions. Well, like a pyramid, right? All right. Silicate material are divided into 2 groups. I always have trouble saying this. Ferromagnesia, right? Ferromagnesian. So it's basically if the silicate, right, which is the silicon and oxygen. If the silicate has ferro is iron or magnesium. If it has either of those or both of them, then that so iron or magnesium, that's considered ferromagnesian. Ferromagnesian. It's fun to say some of these things. All right, and then these things tend to have high densities, right? Because iron has a high density, and so does well, not quite as high, but magnesium also has a relative not as high as iron, but it has a higher density than stuff like aluminum or something like that. They tend to be dark in color. And then the other class. Remember, you're talking about 90% of the minerals you find in the earth are silicates, and so you get the ferromagnesian, and then the non-ferromagnesium, right? So there's no iron or magnesium in either of them. These tend to have lower densities. This is like the average. I would say the average rock that you pick up. If you pick up a rock and it doesn't feel very heavy, just a normal, just a little stone or something like that, and it's relatively light in color, more than likely it's one of these magnesian, non-ferromagnesian silicates. All right, so here's some. So this is the vast majority are these. Let's see. So the non-silicate minerals that only make up roughly 8% of the Earth's crust are carbonate minerals, calcite and dolomite, oxide minerals. So these are the type of ores. So hermanite, magnetite. Magnetite's actually really important because that's actually how we humans originally figured out there was this thing called magnetism. All right, so that's where that, and chromite. All right, so these are sulfide minerals. So there's going to be some some sulfur molecules in there. Anyhow, pyrite, which is also known as fool's gold, and galena. All right, so you'll see examples of this in lab. The sulfate. Let's see. So sulfate is like SO4. I mean, you don't have to remember the chemical compositions. And sulfide is SO3. Just to let you know, that's how these two are different. So that's gypsum, as we mentioned before. That's what we find in drywall, right? The walls that most of us have around in our houses or apartments. Anhydride. Anhydrate. Sorry, I got to say that right. Halide minerals. Of course, halite and fluorite. Fluoride, of course, you use to make toothpaste, right? And a lot of this stuff is it's used for various things. I mean, look, we know gypsum's is used to make drywall. And then, of course, gold and platinum, and of course, iron. Iron is used all the time. They call so if it's just the element by itself, and not some chemical mixture of like this one right here, the sulfates are some mixture of SO4 with something else, right? If it's just the atom by itself, they call it a native element, like gold, or you can find that on the periodic table: gold, platinum, and iron. Iron is element 26. All right, so here's a nice question. The silicates the most common and abundant mineral groups. We know that already. It's like almost 90%. Because silicon and oxygen are, well, let's look at that. They're the hardest elements. No. We'll come back to B in just a second. They're found in the mineral quartz. I mean, that's true, but that's not why. They formed they form in a tetrahedral